Hello, guys. Today we're going to talk about how to solve work energy problems for rigid bodies. And so the steps we're going to learn are very similar to the steps you learned for 4B, work energy equations for particles. So we're going to go through each step together. So first step, and as always, draw your free body diagrams for each rigid bodies. And but in work energy problems, you could have two positions, position one, position two. I would want you to evaluate different positions, look at which position gives you more forces, and draw the free body diagram with the position with more forces. And step two is set up your coordinate system for each rigid body. And step three is to write forces in vector form for each rigid body. Step four is pretty standard, write your acceleration vector for each rigid body. But this acceleration vector must be the acceleration at the mass center, center of mass G for each rigid body. Keep that in mind. That must be AG vector. Step five is to apply Newton's law equation F equals mag for each rigid body and find scalar equations from each Newton's law. So from each Newton's law equation, you can get two scalar equations. And step six is to apply Euler's second law to each rigid body. And from this vector equation, you can only get one scalar equation. So step five and six should help you find scalar equations. And something to pay attention is you will need to apply Newton's law and Euler's equation to each rigid body separately. Please do not sum all of them together in one equation. You're going to find a hard time to do that. Make sure you apply those two equations to each rigid body separately. Okay, so when you apply Euler's second law, this equation, this is a full equation. In another, in the lectures from 5A, we talk about there are three different cases you can simplify this equation. So you need to pick a special case to do your Euler's second law calculation. And in your homework or exam, you will need to mark which case you used for Euler's second law. Okay, so far step 1 to 6 are exactly the same as 5A. Start from step 7, and we need to create a table for kinetic energy. And depends on how many masses or how many rigid body you have, you need to include all rigid bodies. And for each rigid body, to calculate their kinetic energy, and you want to use the full equation. Again, here, please pay attention. In chapter 4a, the kinetic energy calculation, very easy, 1/2 mv squared. In chapter 5b, it's no longer that easy because we have rigid body, things can rotate. So the full equation to calculate kinetic energy has two parts. The first part considers the translational kinetic energy. The second part considers the rotational kinetic energy. And of course, you can simplify this equation. In another video, we're going to talk about what are the two special cases you can simplify this equation. Again, you need to label and mark which special case you need to use to calculate kinetic energy for each rigid body. And step 8 is to create a table for your potential energy. And those potential energy are going to come from all your weight forces and spring forces. And you need to make sure mark your zero reference for each rigid body so that you can put their potential energy according to their zero reference. And something to pay attention is, since here we have rigid bodies, so it has size, dimension, geometries, sometimes can be hard to figure out what's the change of height, delta H. So one trick would be you can always measure what is change of height from the change of center of mass position. Okay. Then the third table will be your work done by other forces, other non-conservative forces. So UNC 1 to 2 is going to come from your friction force and normal force or other constant forces. And something special for this chapter is um, usually friction force, it's a negative work, going to do negative work, right? But if you have a disk with a no slip condition, this disk is rolling, and the disk, if you draw free body diagram for a rolling disk with no slip, you're going to have friction force, Ff, acting at the contact point. If there's no friction, you can't have rolling action. So friction force is required for any roll, no slip rolling um, rigid body. But the work done by this friction force gonna be zero. That's a special case to remember because as we learned that contact point is called IC, instant center. Instant center has zero velocity. So this friction force is acting at a point with no velocity. If the point has no velocity, which means there's no distance traveled, no matter how long um, this disk is rolling. So work done from friction force gonna equals Ff times zero distance, which is gonna be zero. So that's a special case to remember for this table in step 9. Right, step 10 is to apply work energy equation, and you can find one more scalar equation from work energy equation. In step 11, that this will be an optional step. So if you need more scalar equation to help you solve unknowns, you will need find equation from chapter 1 to chapter 3. But usually you will need acceleration equations or velocity equations from chapter 2 for rigid body kinematics. Okay, so those are the 11 steps that will get you through to solve any problems in this section 5B.